So this is a very short overview of the Cray math library. So it's MKL, the math kernel library is from Intel, and of course Cray has we have a different library. So we provide the math kernel library. Here you see basically what we have, okay? Our library is not bound, of course, to just the Intel CPUs, okay? So there is also the version for the previous version, so the AMD version, there's a Sandy Bridge version, so optimized for Sandy Bridge. Also, here is not shown, but there is also a version for the accelerator, so we target the GPUs, okay? The NVIDIA GPUs, okay? So this is the idea, so I will give you an overview of what we can do with this library. We show you the results for GEM, basically, okay? The Cray Blast, basically. The Lapback, the Scalability version, FFT, and then some specific library for coming from Cray, okay? So the idea behind the library is that the beginning was just to collect basically functions inside the packages, basically, and then you just link to these packages. Now it's a little bit changing the idea. So the idea is to have a libraries that where you can get functions which are really optimized, okay? So you can link these libraries not just because you want to call the function, but because you want to call the best function, okay? The best version of this function. So it's a collection, or in this case, where you can have different versions optimized for your system and so on, okay? So this is the special version for Cray. So we do performance specific for the node, so inside the node, but in general for the cluster, okay? So we optimize for a given cluster. And we optimize for scalability. We optimize, of course, for getting performance using vectorization and so on. Okay, so these are description of why we do this work. Okay, so I will give you some details later on how we do, for example, auto tuning. So we provide you a special version of the library, in particular in the case for GEM, for the Sandy Bridge system. Okay, so that you can get the best performance. Of course, we do the comparison with MKL, and of course, if we go slower than MKL, then we need to improve, okay? So we are at least best as MKL, okay? We can be better than MKL, of course. Right, so this is an overview of the function we have. So we have FT, so the FTW, the Cray version of FT, adaptive FT. Then we have the sparse calculations here, and also the dense part, okay? So this is just the meaning of what are these things. I will describe you all these three parts basically in just short overview, okay? So how to use this library, it's very easy, right? So you need to load, you can just link this library in your code basically. So there is a way to use the parallel version using OpenP. You just set the number of OpenP threads in this case. Then there is a way to understand if you, this is the library, okay? If you have the parallel version or not. It depends if you are calling, for example, inside the OpenP region, then you will use the sequential portion, otherwise you will do nested parallelism, okay? So this is the idea. For FFT, here is out of the box. Just link, and you will just use it. Here, FFT, you need to load the module, okay? Module load FFT, and then you can use in your code. And same from here, okay? PET-C and Trillions, okay? And for this library here, you don't need to change anything in your code. Okay. All right. There is, these are the good friends. So you load the programming environment. Then this fantastic tool here. So here, this output when you run without any command. So, okay, you will get this output here. And then you can specify one of these libraries, and you will get more information. Of course, for the other things, you can use the main pages. This is just to remind, okay? And this is the main page for the LibC library, okay, where you can get this information. All right. So you need to check if you are using the correct library. That's, there is a way to specify where you are calling this function. You don't need to add this guy here. This is automatically done when you load the program environment, okay? So no need to explicitly link into this library, okay? So then you can use this option here, and of course, this is the -y. You can resolve where is this library is coming from, okay? To make sure that we are using the version, otherwise it will use the last version, okay? So if you are linking different libraries, it will use the version which is linking from, it will link to the last version of the particular function you are using, okay? All right. So as I say, for trading, we will use OpenP. and you can specify how many OpenP threads, and then of course you can run the libraries using OpenP. Depends if you are calling inside or not an OpenP region or MPI region, then it depends if you will use on the scalar version, so not the sequential version, sorry, or you will use the OpenP version. Here is a description of what's going on, okay? So let's say if you are coding in a code which is not threading, then the BLAST will use OpenP, okay? Will spawn different threads, so we'll go in parallels if you are using dgem, for example, okay? If you are using threaded code and you are outside the parallel region, then still we'll use OpenP threads. Otherwise, we will use the single thread version. This is just to avoid that we are using the nested parallelism, okay? So you will understand that we are already inside the parallel region, and it will not do again OpenP. Otherwise, it will do nested parallelism, okay? So you can easily understand how it works. So a large set of applications, they use basically BLAST. So they use Lapback, and of course we optimize for this vector. So linear solvers, eigensolvers, Scalability, and CZLFT. All these things here are basically based on gem. Okay, so we optimize gem specifically in our case. So we do the best we can do for gem, and for this case we support then all these systems which are basically on gem calls. Okay, so what do we do? Essentially, we take a possibility to, depending on the system, we take the code, we do auto-tuning, okay? So we optimize the code for the particular system, and every time there is a new system, we do auto-tuning again. So in the case of Intel, there is MKL, they do the same thing, basically, right? So you can link to MKL. In our case, we just do the same thing, and we do auto-tuning of the system, basically. And it's very hard then to do auto-tuning, because it depends which version you have, right? So if you are doing matrix, let's say, keep in mind gem matrix multiplication, let's say double, okay, dgem. So then you are doing a case, it depends, strongly depends, the optimization you are doing of the sides of these matrices, okay? So there is not a real rule that you can say, okay, it's valid for any kind of dimension. And here is the case, okay? So let's say if you are taking the matrices like this, you can do this optimization and you will get the best from this very easy case where all three matrices are the same, basically. They are square matrices. But in reality, we have cases where we have something like this, okay, with small m, okay, m is the dimension here, or you have small n, or you have small k, okay, which is the dimension for b, okay? So we need to optimize for all the possible dimensions, okay? There is no real case, unless we are targeting a specific case, then maybe it's better if you write your code, okay? For all these cases, you need to provide the specific kernels, okay, for this matrix multiplication. So how to do that? As I say, use auto-tuning. There is a package you have inside, which is called BFrame. This package is basically what it does. It starts for a given combination, then you can imagine the matrix multiplication based on loops. Then it starts to apply optimizations in the way that it's doing a rolling, in the way it's doing blocking, all the possible optimization that we understood in the last days, okay? This is the way how it works. So you have starting from a given version of the code, the kernel for that given dimension, as I say, okay? Then you start all this optimization. At the end, you get the fastest possibility for this matrix multiplication, and you store inside the library. And we do all this kind of auto-tuning for each new system, okay? So at the end in the library, you will get the fastest possible kernel for that combination, okay? It's quite clear, okay? So this is the comparison between running on the Sandy Bridge single thread between MKL and our version of the code. As you can see, we are slightly better, okay? And this is the dimension, MN, K, okay? But as I told you, this does not depend on the dimension. So for each dimension, we have optimized the kernel, okay? Of course, you can imagine auto-tuning is quite slow procedure because you need to run all the possible combinations, get the best, and then store the best, and so on. But then you run once for a given system, and then you store in the library, and you ship the library. That's the end of the story, okay? This is for large, this is small, MNK, and this is for large MNK, and still you can see that in most of the cases we are better than MNK. So for this Sandy Bridge system, of course, we do the comparison with MNK, okay? All right. Of course, we try to do the best for any kind of combination, but if you have a specific case, for example, I like to do this matrix multiplication between a given dimension, okay, and maybe you will not get the best from our library, you can send this request, and then we can work to to improve and then add a new version to the next library. Okay, that's the conclusion. So in this way, we do optimization, so we try to have the best combinations, the best performance on top of this library. Now, let's move to Lapback, threaded Lapback. So works exactly as BLAS, basically. Depends, is using OpenP threads. Depends if you're running inside a parallel region or not, then it will use OpenP, you will get the best on the node, okay? So essentially, it uses BLAS at the end. So it's basically nothing to say here. And of course, then you can apply if you are inside the node, you can apply the OpenP parallelization or not, okay? For Scalapack, in this case, it's still optimized for Gemini. It's still missing the optimization for the new network, but they are working hard on that, okay? So you can imagine there is good scalability. It's also based on optimization from BLAS, okay? And then there is this guy here I will show you later on, which is a way to include a single precision, double precision, mixed way so that you can get best performance on this system. And here you can see the comparison where you are comparing the two libraries, in this case in a big system, okay? Still, this is for the Cray XE, so the ROSA system, basically, if you like. So you can see that we still have scalability, okay, with a large number of nodes, okay? As I say, this is still working on for the new system, but we will see soon these numbers, okay? So interactive refinement toolkit, as I showed before, is a way to use inside these libraries, inside the possibility to have a single and double precision. All, of course, reductions and so on are done in double precision. So in most systems, you have a factor 2, okay? You can imagine that in AVX, 256 bits, you can have 4 doubles, but you can have 8 single precision numbers, okay? So if you are in a world where you are using vectorization, but all the other systems basically have factor 2, okay? You're using vectorization, you can gain a lot if you move to single precision. And then there are specific optimization for single precisions, okay? The point is that you don't want to lose, of course, precision, total precision. So you need to pay attention where to put single precision instead of double precision, okay? So this tool is able to understand this is interactive, so you will understand where to put single precision to gain. So you can use this tool, here, this explanation how it works. So it's quite easy, basically, there are APIs to use, okay? So you will change from this function here to this function here. This is just an example how it works, okay? Then you will set this variable here, and you will run, and this is just a comparison, okay? So what we expect is a factor 2, and here you can see the effect, okay? So, as I say, mixture between single and double precision, okay? These peaks here, randoms. I don't think it's a real problem, okay? It's nothing special, okay? So, of course, this is not part of MKL. As far as I know, there does not exist anything like this, okay? So anyway, so this is just to get the best performance. This is still an AMD system, but of course, the same thing applies for the Sandy Bridge. FTW. So basically, we interface to FTW. So as I said before, you just do module load FTW, and then you can use the FTW. There is also a Cray version, okay? Here is a comparison, but as you can see, the MPI ranks basically for the two versions of FTW, okay? So it's just linking to this library. And then, as I say, there is a Cray version, okay? So in this case, it's parallel version, and you can have all the information from the main page, in this case, okay? And also in this case, you can, I don't have the plot, but then you can do comparison, basically, over the results. So this another library that you can use, okay? Last thing, I guess, is the Cray Adapt sparse kernel. So you can use this for sparse matrix, basically, okay? And also in this case, they are optimized for the system. So we do also in this case auto-tuning. Here you can make the comparison between the two systems, or still on Intel Sandy Bridge, okay? So we are here for our system and the PET-C, okay? Same thing for a different version, okay, with the trilineals and trilineals. Also in this case, we are much better than the standard version. So we do optimization for the specific libraries. Then here at CSCS, we have an expert of LibC, the math part. So if you have special requests, just send to him adjunctate, okay? And he can answer to your questions how to use these libraries. It was just a short review, okay, nothing special. So this is a very short overview of the Cray math library. So it's MKL, the math kernel library is from Intel, and of course Cray has we have a different library. So we provide the math kernel library. Here you see basically what we have, okay? Our library is not bound, of course, to just get functions which are really optimized, okay? So you can link these libraries not just because you want to call the function, but because you want to call the best function, okay? The best version of this function. So it's a collection, or in this case, where you can have different versions optimized for your system and so on, okay? So this is the special version for Cray. So we do performance specific for the node, so inside the node, but in general for the cluster, okay? So we optimize for a given cluster. The results for GEM, basically, okay? The Cray Blast, basically. Lapback, the Scalability version, FFT, and then some specific library for coming from Cray, okay? So the idea behind the library is that the beginning was just to collect basically functions inside the packages, basically, and then you just link to these packages. Now it's a little bit changing the idea. So the idea is to have a library that where you can the Intel CPUs, okay? So there is also the version for the previous version, so the AMD version, there's a Sandy Bridge version, so optimized for Sandy Bridge. Also, here is not shown, but there is also a version for the accelerator, so we target the GPUs, okay? The NVIDIA GPUs, okay? So this is the idea, so I will give you an overview of what we can do with this library. We show you we optimize for scalability. We optimize, of course, for getting performance using vectorization and so on. Okay, so these are description of why we do this work. Okay, so I will give you some details later on how we do, for example, auto tuning. So we provide you a special version of the library, in particular in the case for GEM, for the Sandy Bridge system. Okay, so that you can get the best performance.